Hello, everyone. I'm very happy to host Ido Greenberg. Wait, some few words about it.
I thought you want a selfie.
Ido, what?
I thought you want a selfie.
Ah, yeah. Okay. Ido is a Technion alumnus with 10 years of industrial and academic experience in algorithm research and mathematical modeling and machine learning. He's currently a PhD candidate with the Technion under supervision of Professor Shimon No, and his research focuses on making reinforcement clearing work better in the real world. Today we'll talk about detecting rewards deterioration in episodic reinforcement learning.
Yeah.
So Ido, the stage is yours unless you want a selfie.
Thank you very much. So yeah, we're gonna basically talk about a statistical test to make sure that our reinforcement learning agent performs well in production. We'll begin with an overview of 15 minutes, and only then you may choose how deeply to attend the technical details. So yeah, we're going to talk about reinforcement learning, but not about how to train the agent to perform as well as it can in the environment, which is most of the work in reinforcement learning, but more about, usually we need to stop training the agent and only then we can move on to production. And we want to make sure that in production, everything goes well at any point of time. And that's very important in risk-sensitive tasks like autonomous driving, where we must be able to tell at any point of time that our vehicle doesn't begin to drive to weird directions and so on and so on. Or for example, if we train a cheetah to run as fast as it can, and each time it starts running from scratch and builds its velocity and keeps it, and at a certain point, the gravity suddenly falls, and then the performance of the cheetah deteriorates accordingly. Then we want to be able to tell that as soon as possible because we hate when it happens. And once we notice the degradation, we can stop the running, or maybe send the data to diagnosis, or maybe take manual control. There are plenty of things we can do once we notice the problem, but noticing the problem is a major bottleneck for handling the issues. Now, the thing is, it's not that simple to notice that something is wrong. For example, take the upper left figure, where suddenly at a certain episode, we work in episodes in reinforcement learning usually. At a certain episode, we see that the speed drops. Probably the cheetah fell down because no cheetah is perfect. But actually, I didn't change anything in the environment in this scenario. So it's just part of the variance of the problem. On the other hand, on the bottom left, I essentially increased the electricity bill, and so we have a slight drop in the rewards of the cheetah, but it's really hard to tell that from the figure. So we would like to know when we have an actual problem that we need to attend, and when we are just within the variance of the performance, of the valid performance of the cheetah. So fortunately, someone has already thought about this kind of problems, and it has a name. It's called statistics. So we would like to take our question about whether the rewards are smaller than usual. The rewards are you may say, the scores of the agent in reinforcement learning. We want to know whether they're smaller than usual or not. So first of all, we want to write it in statistical terms. So first of all, we need to say what is usual. And that's pretty straightforward. We can assume that we have a reference data set of valid rewards to compare to. For example, if we train the agent and then we tested that everything is fine, so the rewards that we observed in the test, they're probably valid, otherwise we wouldn't move on to production. So that's a reference data set of valid rewards, so we can compare to it. More tricky part is that statistical tests usually assume that the signal is i.i.d, identically distributed and independent. And we can see here that the rewards of the agent, for example, in half cheetah, in different time steps of the episode, they're not independent. we can see that the correlations are higher than 0, even when the time steps are not identical. So we have dependencies between the time steps. Now there are certain statistical tests that assume different models with correlations. A popular framework is called autocorrelation, where we assume that there is correlation, but it only depends on the time difference. But we can see that here that's not the case either, because the correlation between time step 0 and, for example, 100 is not the same like the correlation between 600 and 700. Okay, so we have a quite complex structure of correlations here, and the statistical signal is quite weird. And also on top of that, in addition to not being independent, it's also not identically distributed, because the beginning and the end of the episode look very different from one another. So that's an issue, but the natural solution would be to say, well, okay, maybe the time steps are not i.i.d, but we work in episodes, and we can say that we can assume that every episode is taken from the same new distribution, and the episodes are i.i.d. And then we can just take one number per episode, for example, the average, and the averages of the rewards of the episodes, they are i.i.d, so we can apply standard statistical tests. Okay, how would that look like? This slide essentially explains the concept of bootstrapping. So we have the reference data set of many episodes, and now we sample, for example, H random episodes. For each one, we have only the average of the episode, and we take the average of them. Okay, and what we receive is an example for a valid average reward over 3 episodes in this case. Okay, now we repeat this procedure for, I don't know, like B times. And now we have a distribution of this value, the distribution of a valid reward of 3 episodes. Now we run in production, and at a certain point of time, we want to ask whether the performance in the last 3 episodes is valid or not. So we just calculate the mean reward, and then we can compare it to the distribution that we built before. And if it's very small, like to the left of the distribution, we say, well, something is probably wrong, because this average, it doesn't seem like it got from the same distribution as our reference data. So what I've just described here is bootstrapping. And what allowed us to do it is that we reduced the t-dimensional signal of the rewards of every episode. We reduced this to one-dimensional signal, which is the average of the episode. Okay, and then the samples are i.i.d, so we can resample them in order to build the bootstrap distribution. So that's cool, and that's statistically valid, and it would work. The thing is that when we reduced the dimension of the problem, of the signal, we lost a lot of information. And this will result in reduced statistical power, that is the probability that we actually detect a problem when it occurs, the probability reduces. Now let's get convinced that this is an actual problem, and not just a hypothetical one. So for example, in half cheetah, we see here the variance of the performance over the time within an episode. So in the beginning of the episode, we see that we have mostly no variance. The cheetah runs the same thing every episode. And later, in the end of the episode, we have a lot of noise, a lot of variance, because sometimes it falls, sometimes it fails to accelerate until the end. And now imagine that we have some problem that causes a drop in the performance, a slight drop in the beginning of the episode. So that's a quite strong signal, because we don't have drops in the beginning of the episode. We have very stable performance. But if we take the average over all the episode, we essentially average this strong signal with the noise that is in the end of the episode. So we might lose this signal and not be able to detect the degradation. So what we suggest to do, instead of taking the simple average of the rewards per episode, we offer to take a weighted average, where each weight of each time step is simply the inverse variance 1 over the variance of the performance of that time step. Okay, the intuition is that if we have a noisier time step with a larger variance, then we want to give it a smaller weight in our calculation. So then we can take the weighted average and we can check if it's smaller than a certain number. That's called a threshold test. And if it is, we say that there probably is a problem. Now we show that this test, not only it's more powerful than taking the simple average, powerful in statistical terms, like the probability to detect a problem, it's even optimal in the sense that given a significance level, given a certain level of false alarm rate, we will have the best possible power. No other test can perform better than that. And that's a very interesting result, and that's actually our main result, because we don't need to look for more complicated tests and sophisticated methods. We can just take the very simple weighted average, the rewards. It's computationally as simple as using the simple, the naive simple average, and we have the best monitoring we can achieve possibly. So that's the main result, and in addition, we don't only show that it's more powerful than the simple average, we also show by how much. Essentially, it is that when the variances of the different time steps are more heterogeneous or more different from each other, then we have more advantage over the simple average, which corresponds to the, yeah.
Can you explain under what assumptions this thing is optimal?
Yes, we need to assume that the rewards are normally distributed, and we also define the way the rewards look like and the way the degradation looks like, and that's what we do in the after the overview in the part of the.
So you assume that the vector of rewards is a multidimensional Gaussian distribution.
Yeah, basically yes, and we will define it well within a few slides. Yeah, so that's the main result, and that's the way that we deal with the fact that the signal is not i.i.d, and we deal with it without losing more information that we need. And the third issue is that we repeat this test over and over again, so we're bound to have false alarms eventually, and we would like to control the rate of the false alarms, not to have too many. So basically we use bootstrapping again to control the false alarms, but again we need to sample not time steps because they are not i.i.d, but episodes. But then what happens if we're in the middle of an episode? So we need to sample it carefully, and we show in the paper how to do that. Eventually it works. So that's basically it. And now we can see how well it performs. So every figure here represents a scenario, a benchmark in reinforcement learning, where we modified something in the environment, so the performance deteriorates. And then we take each color is a different statistical test. Those three are variants of our test. And we see, for example, that in this case, in half cheetah, when we increased the cost of electricity, then after 10,000 time steps, the probability, the standard tests like the simple mean and two other variants, they detected that there is a problem only in a few % of the experiments that we ran. And our test detected the problem in between 40 and 70%, depending on the variant, and we see that it goes to 100% soon enough. So in all of these examples and in most of the other examples that we tried, we saw a significant benefit to using our statistical test to detect problems. So that's basically it. We have a statistical test to detect problems in an agent of reinforcement learning after we finished training it. And we see that this test is empirically faster and more powerful than standard statistical tests. And we show that it's even optimal under certain assumptions. And we also can control the false alarm rate of this test, even though the data that we run on is not i.i.d. Now, before I move on to to the more technical parts, I will just mention that all of this work only considers the signal of the rewards of the agent, and it considers it as a time series that is function of the time. And we could, for example, for those of you who are familiar with reinforcement learning, we could use other available information like the value function or the temporal differences. So we could consider them. Or alternatively, we could, instead of look at the rewards like a time series, we could look at them as a function of the state of the state of the agent in the environment. And then, for example, if we are in a in an episode when we happen to have better states, then and the performance, the rewards are okay, then we could actually notice that something is wrong. In our test, the rewards are okay, so there's no problem. But if we condition on the state, then we may notice more issues. And another direction is, instead of looking at the performance, looking at directly at the dynamics of the environment. Okay, that's essentially the state transition in the environment, and look for anomalies there. So we have certain ideas for all of these directions, and whoever of you is interested in research in statistical methods related to machine learning in general, welcome to talk to me. So that's basically it. We are going to dive into the analysis of into the definitions and the analysis of the statistical tests. And if you have any questions, that's a good time. All right. Yeah.
You said you are testing on episodes, and you showed your time. Could you tell us what's the mean episode steps? How many steps you have per episode?
Yes, in half cheetah we have 1,000 time steps per episode, I think. In humanoid it's several hundreds, and in pendulum I think it's 200. And the duration it takes you to detect the issues, it depends on the amount of the degradation, right? So in this case, in certain, I think in some of these examples, you have detection like within 1 or 2 episodes. If you had stronger problems, more severe problems, you would detect even within the first episode. And in other problems, we do only a slight degradation. So it takes many episodes to detect. Okay. Yes.
Is there growth in the falsehoods that you detect with your method?
I'm sorry, I can't hear you.
Is there growth in the falsehoods that you detect with your methods as opposed to the standard methods?
Growth in what?
False detections.
No, all of these tests, yeah, I didn't mention it. All of these tests are tuned using exactly the same Bootstrap method to tune the false alarm rate. So all of them have exactly the same, or roughly exactly the same number of false alarms when we run them on the null hypothesis, on the environment without the modifications. Okay, cool, good questions. So, sorry. We're going now to define what the signal of the rewards look like. And we're going to define what the degradation looks like. And then we're going to derive an optimal test to detect that degradation. So the signal of the rewards, we model it as what we call an episodic signal, which is just a sequence of random variables. We conceptually separate this sequence into intervals. Each interval is it corresponds to an episode of length, for example, t. And we assume that the rewards, the random variables within the episode, they are modeled by the joint distribution. We call it F, and we basically assume nothing about it. Everything can happen within the episode for now. And we assume that every such sequence, every such interval, such episode, it has the same joint distribution F. Okay, so the episodes are identically distributed, and the whole joint distribution of the whole n-dimensional signal, it's just the product of all the all the distributions, all the probability density functions of the single episodes. Okay, so since the whole joint distribution is a product of the episodes, we essentially assume that the episodes are independent. So together we get that the episodes are indeed i.i.d, but within the episode we try not to assume anything about the distribution. We also may have this marginal distribution if we're in the middle of an episode, the marginal distribution for the first time steps in the episode, and that's the red part, and that's a technical issue. Now we can consider the first moments of the,
Not learning during the episodes?
One?
You're not performing learning during the episodes?
No, as I mentioned in the beginning, we assumed that the agent finished to train, and now we had to fix it and send it to production, and that's a pretty realistic constraint in many applications, especially risk-sensitive applications where you need to, you are not allowed to do any changes in production. Okay. So now we can consider the first moments of F, the distribution of the episodes. We call them mu0 and sigma0, the mean and the covariance matrix of a single episode. Their dimensions are t and t squared. And if we have a sufficient number of episodes, we can use it to just estimate them. Okay, so we don't deal here with the accuracy of the estimation. We assume that we have many episodes and we can estimate them accurately. And once we know the mean and the covariance of a single episode, we can have the mean and the covariance of the whole n-dimensional signal just by repeating them over and over. Okay, they are n and n squared dimensional. But they essentially, for example, the mean is just repetitions of the means of the single episodes. Okay, so now we have the definition of an episodic signal, and we can go on to define our null hypothesis, which is that no change is applied, and that basically we model as the rewards is an episodic signal with known parameters mu0 and sigma0. We could estimate them from the reference data set. And we add the assumption that the rewards are normally distributed. Okay, at this point we add this assumption, later we will relax it. So essentially the probability density function is this thing, some constant depending on the covariance matrix, and and this exponent, which is just the multivariate normal distribution. We have here the sigma0, and mu0 is within this x tilde. That's our null hypothesis. And now we defined how a degradation looks like. So we assume that there is just a vector of epsilons, which are reduced from the average, from the mean of the distribution. Okay, so instead of mu0, we have mu0 minus epsilon. And for the following theorem, we are going to assume that the degradation is uniform in the sense that this vector is constant vector of ones times only a scalar epsilon. Okay, so we have a small, or we have some drop of epsilon in all the time steps uniformly in the performance of the agent. That's what the corresponding distribution looks like. It's essentially the same. We just replace the x tilde with, we add this constant vector to it. Now, we want to decide whether we live in this world or this world. So we have a nice lemma in statistics called Neumann-Pearson lemma, which says that if we take the ratio between these two, okay, between these two expressions, the likelihoods of the data given the different two hypotheses, we take the ratio between them and we compare it to a certain threshold. Then this is, and if we are lower than the threshold, we say that there is a problem. We declare that we reject the null hypothesis and say that we detected a degradation. This test, given its significance level, the probability of a false alarm, given the null hypothesis, that's determined by the threshold that we set. And given that significance level, this test would be optimal. Okay, so that's Neyman-Pearson lemma, that a likelihood ratio, threshold test over the likelihood ratio is statistically optimal. And if we calculate this likelihood ratio, then this constant, since we assume here, I didn't mention it explicitly, we assume change in the expectation, but not in the covariance matrix in our degradation model. So this constant cancels out, and we only have the exponent, and the ratio becomes a difference. And we can actually take the log of the likelihood ratio because having a threshold test on some random variable is equivalent to having a threshold test on any monotone function of this variable. We just need to tune the threshold. So after taking the log, we just remain with this expression. So we just need to calculate this given the data that we observe and compare it to a threshold, and it is guaranteed that this test will be optimal in terms of statistical power. So let's clean the board and see what we get from this expression. You may notice that x only appears here in this expression. This is a constant, it doesn't depend on x. So we can say that this whole expression is just monotone in this, okay, in this part. But this is exactly as we said before, that's exactly the weighted average of the reward. Because this is simply a vector, this constant once vector times the inverse covariance matrix that reduces to a vector, and we can consider it as a vector of weights, and then we just multiply the weights by the reward signal. And you may notice that indeed if we ignored the covariance matrix and simply took this expression, it would exactly be the simple sum or the simple average. That's the same for that matters. So indeed by considering the covariance matrix, we have a weighted sum instead of a simple sum. And also you can notice that if the covariance matrix was diagonal, okay, like we had no correlations, we still weren't identically distributed because the diagonal was not the same numbers, but we didn't have correlations, we were independent, then this statistic would reduce to this expression, which is just a weighted average where the weights correspond to the inverse variance of each time step, like we said before. So this statistic gives us the optimal statistical test. We name this statistic the test statistic of the uniform distribution of the uniform degradation. Sorry. So we call it SUNIF. And the only thing I said that isn't correct is that I assumed that this is constant, so we can focus only on this and have a monotone function. Now that's not entirely true because we don't assume that we know the amount of degradation epsilon. We only assume that we look for a degradation which is larger than a certain epsilon 0, and that's it. And epsilon can be anything above that. So we need to take the minimum over the epsilons, and the epsilon that minimizes this expression might depend on the data, on the rewards that we observe. So we cannot anymore ignore this term because it may depend on the data through this minimization over epsilon. So in fact, we need to show that the epsilon that minimizes this expression, it only depends on the data X, the data of the rewards, through this statistic that we defined, and that this dependence is still monotone. And then after we substitute the dependence within epsilon, we can show that we need to show that everything together is still monotone in the log likelihood ratio, and then we can apply the test safely. We're not going to do it now. It adds like 1 or 2 pages to the proof, and but eventually it works. Yeah.
But epsilon 0 is constant in all its entries, right?
You know, for what?
Epsilon 0 in your representation is constant in all its entries.
Epsilon 0 is like a hyper constant that we only look for degradations larger than epsilon 0. Epsilon is the actual degradation. It's something above epsilon 0, and yes, it is constant over the whole episode. That's what we call the uniform degradation assumption, which is the title of the slide. And we will relax that later, but for now we assume a uniform degradation. Okay.
So something here is confusing me because the second term, that's just like a positive number that you multiply by. Like the thing you multiply by epsilon squared is a positive number.
I'm sorry, I don't.
The first term, it also seems like it usually should be a positive number because it's something like the average, the weighted average of the report. And as long as those numbers are positive, the minimum is always happens at epsilon equals epsilon 0. So
I don't wait. No, the weights, the data might be negative, the rewards. I mean, the weights are positive, right?
You subtract the mean. So that's
yeah, sorry, x tilde is x minus the is the deviation from the mean. Okay, so it may be negative. Yeah. Okay, any more questions? So that's a nice result. We showed that we only need to calculate the average reward, the weighted average reward, in order to have the most possibly powerful test to detect problems with our agent. And let's recap what we had to assume in order to obtain this. So the rewards are episodic in the sense that they come in i.i.d. episodes. But within the episodes, we don't assume anything, except that we did assume for this theorem that the rewards are normally distributed within the episode. And we also assumed that the way that they deteriorate when they are, the way is uniform over the whole episode. So that's pretty strong set of assumptions. And we would like to relax some of them. So we keep the episodic assumption, but we are going in the next slides to relax the two other assumptions. Okay. So what happens if the rewards are not normally distributed? Now we don't have an optimal statistical test. We can find specific distributions where we should build specific statistical tests in order to be optimal. So our test is not optimal anymore, but usually we don't know the underlying statistical models, so we cannot build the actual optimal test. So it would make sense to compare our test to the default test, which is just the threshold test over the simple average. Okay, so we want to check which one of them is more powerful in a more general framework when we don't know the distribution. So the first step is to notice that each one of these statistics can be written as a sum over the episodes. For example, the simple average is just, we can write it as taking the sum for every episode and then the sum over this, and to normalize it to be an average. So since it's a sum over i.i.d. Data samples, the episodes, it is asymptotically normal. We need to assume the existence of second moments and so on, but it is given according to the central limit theorem, it's asymptotically normal. So let's calculate its mean and variance and standardize it to have zero mean and a unit variance. And then since it converges to a normal distribution, it has to converge to the standard normal distribution after we normalized it, like with mean 0 and variance 1. And since this is the asymptotic distribution, we know that the test threshold, if we tune the test to have a probability alpha for a false alarm, the test threshold will be exactly the alpha quantile, the alpha percentile of the standard normal distribution. Okay, so now we want to ask what happens when we have a degradation in the signal, and to calculate the power of the test, like the probability that we detect the degradation. Okay, so given a degradation, we can show that the variance of the signal doesn't change, only the mean changes. The variance of the statistic, of the normalized statistic. Okay, for example, in the uniform degradation statistic, the change in the average would be, instead of having average 0 like the normalized one under the null hypothesis, now the normalized statistic has an average of minus epsilon times this thing. And now we want to know what's the power of our test, like the probability that we detect a problem, which is just the probability that we are smaller than the test threshold. Yeah, we found the test threshold here. So we ask what's the probability that the test statistic is smaller than this threshold, given that we have a degradation. Okay, but looking at the statistic given a degradation is exactly like looking at the statistic plus this term given the null hypothesis, because we said that the degradation only shifts the average, except for that the distribution remains the same. So instead of writing this, we can add this term here or reduce it here equivalently, and then condition not on the alternative hypothesis but on the null hypothesis. Okay, so now we have this expression. We just want to know what's the probability that our test statistic is smaller than this number. But since we have the central limit theorem, which says that we converge to a normal distribution. If you look up the definition of convergence in distribution, which is what we get by the central limit theorem, it says exactly that the probability that we are smaller than a certain number, it converges to the CDF, the cumulative distribution function of the limit, which is the normal distribution, applied to this number, to this same number. Okay, that's just the CDF of the standard normal distribution, and we apply it to the same number like here. Okay, we have this equality by the central limit theorem, and that's exactly what we need, because now we have the power of our statistical test in terms that we are familiar with. Now notice that if we were in the null hypothesis, the epsilon would be 0. So we would just the CDF of the standard normal distribution applied to the alpha quantile of the same distribution. So that's exactly alpha. And that's indeed the probability that we detect a problem where in fact there is no problem. And since we have a degradation, then we have a larger probability to detect the problem. Okay, so that's cool. That works as we expect. We can do the same exact thing for that was for SUnif, our test statistic. We can do it for the simple average, the original statistic, and we have this power. And now we only need to show that this is larger than this. Okay, so let's rewrite it. That's the power of the statistical power of the simple test, and that's the statistical power of the uniform degradation test. And we would like to show that this relation between them, and I don't have much time, but that's cool, so I will say it anyway. This is essentially multiplying the inverse sigma from both sides by a vector of ones. It's just like taking the sum of all its elements. So that's like the algebraic mean of the matrix, of the entries of the matrix. And here we take the sigma inverse, then we take its inverse back to sigma, and take the sum, and then take its inverse. Okay, so that's like the harmonic mean. And we actually need to show that this is smaller than this, which essentially means that the harmonic mean is smaller than the algebraic mean. But it's not exactly the same means inequality that you're familiar with, because here we didn't take the inverse over the elements of sigma 0 like element-wise, but we took a matrix inverse. So it's kind of a matrix form of the means inequality. And we can actually prove it once we write it correctly. We can prove it pretty straightforward using the Cauchy-Schwarz inequality. And then indeed we have that our test, even without assuming the normal distribution of the rewards, our test is more powerful, at least than the naive test over the simple average. We can also quantify how much it's more powerful. We can just take the ratio between those terms, and we already know that it's larger than 1, but if we diagonalize everything and rewrite it, we can rewrite it in this form, where the lambdas are the eigen values of the covariance matrix. And what we see here is that our power gain, the advantage of our test, it grows when the eigenvalues of the matrix are more heterogeneous, or more different from each other. And if we think about them as the different variances in the problem, then we got the intuition that we discussed before, that our test is, let's say, more important to use when we have less homogeneous episode. Yeah, so that's cool.
Do you have something to say, like, when the number of episodes are finite, not good to infinity, like how many episodes you need in order to get this obvious benefit?
Yeah, so the short answer is no. I use the central limit theorem, which gives me, I don't think it gives me anything about the convergence rate. And I probably need to use stronger tools and maybe also add assumptions if I want, like sub-Gaussian maybe distribution or something like that, in order to say something intelligent about the rate of the convergence.
Isn't it a classical tail-bound question?
Classical tail-bound question is quite general, isn't it? Like
you have some variable, you get a result, you want to know what's the probability that it comes from this distribution. So
that's true, but to say
something like often bound or something like that. Instead of name of Pearson.
That's interesting. For Hoffman-Bound, I don't need many assumptions about this signal, right? And then, yeah, probably it's possible. I didn't try this. I need to think about it. That's interesting. So this is the result for the rewards that are not normally distributed. However, we still had to assume that the degradation is uniform over the whole episode. And as we can see, that's often not the case. When shit happens, it doesn't happen uniformly over the episode. So we would like to relax this assumption and use another model. And the model that we chose was, instead of a constant vector of ones, now we have a vector of ones and zeros. So at certain time steps in the episode, we have degradation, and in other time steps, we don't have degradation. That's not a very realistic model either, but it arguably can approximate realistic models, because now we just assume that at a certain part of the episodes we have a problem. And again, we can calculate the likelihood ratio, and I don't really have the time to follow the whole proof, but essentially we have this expression now. Instead of ones, we have this A vector, which is a combination of ones and zeros, but this term is just a sum over the entries of A. So we don't have to actually calculate a complicated combinatorial problem. We can just sort the entries corresponding to the entries of A, and take the m smaller entries. M is the number of ones. Take the m smaller ones in order to calculate the mean over all those possibilities of the alternative hypothesis space. We do have this term, which we need to, which is more complicated to minimize, but we just bound it by O of epsilon term, and then we can show that this bound propagates through all the calculations. So eventually we have that the statistical power of the test statistic that we suggest, the weighted average over this part of entries, this test statistic gives us the optimal power up to O of epsilon. Okay, so In this case, we need to use a different statistic, and we don't obtain an optimal test, we obtain we can call it a near optimal test, at least for small values of epsilon. Oh, I thought 50 plus. Okay. Okay. So that's basically the summary of our analysis for the different variants of the test. We have, if we assume that the degradation in the rewards is uniform, then if the rewards are normally distributed, we have a test which is optimal in terms of statistical power and is also very simple, just the simple average of the rewards. If we don't assume the normal distribution, then this test is not optimal anymore, but it's more powerful, asymptotically more powerful than the simple average test. And we also quantified the advantage of the power. And if we assume a partial degradation, then under the normality assumption, we need to use a different test, which is near optimal. Now, okay, we have all these variants of the test, and in all of them, there is some threshold that we have to compare the statistic to. The statistic is just the function of the data, need to compare it to the threshold, and the tuning of the threshold will decide how many false alarms we will have. So we would like to control this somehow, like, for example, within H episodes, not to have a false alarm with probability larger than alpha 0. So for that, we just use a Bootstrap algorithm to simulate many sequences of episodes. Okay, in each Bootstrap iteration, each time we sample certain episodes, and then the episodes that we sample, we simulate a sequential test over them. How we simulate a sequential test? We just run the agent over the episodes, and at certain points of time, we apply we call it the individual tests. Like within every sequential test, we have many individual tests for degradation of the signal. Each time it's for the few last episodes. And for each such individual test, we obtain a p-value. A p-value that tells us whether we believe that there is a degradation or not. And the trick here is that in order to decide whether there was a detection of degradation in the sequence or somewhere in the sequential test we detected a degradation or not, we only need to consider the minimal p-value among all the individual tests. Because if that minimal p-value is smaller than the threshold, then in that individual test, we had a detection of a problem. And if it's not smaller than the threshold, then all of the p-values are larger than the threshold, so we don't have detection of a problem. So we only need to keep the minimum p-value for each such sequence. And we do that for every Bootstrap iteration, each time we sample different episodes. So we have now a bunch of many minimal p-values, and we can just take the alpha 0 quantiles of those minimal p-values such that exactly alpha 0 of the minimal p-values are smaller than this number. So in exactly alpha 0 of the Bootstrap iterations, we would conceptually have a detection of a false problem. So this gives us exactly what we need, the control of probability of alpha 0 for a false alarm within the sequential test. Now, a nice property of this Bootstrap procedure is that when we loop over the test points, we can loop not only over time, but over other things as well. For example, we can loop over different statistical tests. We can calculate for each point of time, both for example, we can calculate the partial degradation test from the previous slide for different hyperparameters of the number of ones. Yeah, we had the number of time steps where we have degradation. Or for example, we can run together the uniform degradation test along with the simple average that we'll see in the next slide, which may be beneficial. So that's a nice property. And this indeed connects exactly to this issue in the slide when our test may fail. if we have a very non-uniform degradation, we had the model of partial degradation, true, but there may be a very weird behavior of changes in the environment. For example, what happens if the rewards increase in certain time steps, but decrease in others? So our models don't capture this situation very well. So to stable our model, we could just run it in parallel with the simple average, with the naive test, and our bootstrap method allows us to control the false alarm of the two of them together. So that's a nice practical property. Another issue is when the rewards themselves have a very non-smooth distribution, we may say, or for example, if they are very sparse in the space of the time steps. So it might be difficult to estimate the mu0 and sigma 0, the parameters of the distribution. So to solve this, if we see that the distribution is problematic, we can just downsample the signal. Instead of 1,000 time steps, we can divide it separate it into like 40 intervals of 25 time steps each. And then everything is smoother and easier to estimate. And then the only thing that we essentially really need to assume is that the setup is episodic, that we have multiple i.i.d. episodes that we can estimate our signals from. So that's the actually strong assumptions that we use here. And this assumption, it's satisfied for many different problems, and in particular it's very standard to assume in reinforcement learning. And that's actually one of the main reasons why we put this whole problem in this whole work in the framework of reinforcement learning, because you may notice that in fact you can apply our statistical test to any episodic signal that you look for degradation in, even if it's not coming from reinforcement learning, as long as it consists of episodes. So that's it. We have a statistical test to detect the degradation in the performance of an agent or any other episodic signal. Our test is statistically optimal under the assumptions of normal distribution and uniform degradation. It's empirically fast even without these assumptions, and we can control its false alarm rate even though the signal is not i.i.d. So that's it. Thank you very much. Yeah, if you have any more questions.
Okay, so thank you again, Ido.
Thank you.